Hi, my name is Myles, and I'm a postdoc at the University of Florida in the Precision Space Systems Lab. At UF, we are developing the Charge Management Device, or CMD, for the LISA spacecraft. This effort is part of NASA's contribution to the LISA mission, and will result in a delivery of a TRL-6 CMD to ESA, developed to flight readiness by our industrial partner, FiberTech. In this video, I will go over what the CMD is and what it must do, followed by an overview of our current TRL-5 design and an update on its development. Okay, enough logos. Let's get into it. Let's start by bringing everyone up to speed by quickly going over why the CMD needs to exist. I am not going to go over the full LISA system. Instead, I'll just focus on a single part, the test masses that form the end mirrors of the laser links between the spacecraft. It is with these test masses that we detect the stretching and squeezing of spacetime by carefully measuring the distance between them. I don't think that I need to tell anyone watching this that making a gravitational wave measurement is a difficult task. And one of those difficulties is keeping these test masses shielded from everything that isn't gravity itself. Consider the test mass, happily floating in space, following the spacetime geodesics in its orbit around the Sun, just as Einstein intended. However, if left unshielded, it is subject to buffeting from the solar winds from the very thing it is orbiting, or even interfered with by external magnetic and electric fields from those in its orbital neighborhood. Thus, it is the job of the gravitational reference sensor to house and isolate the test masses from the surprisingly noisy solar environment. Unfortunately, there is one source of noise that does not particularly care about our feeble attempts of shielding: high-energy particle radiation. When a high-energy particle originating from the Sun or cosmic rays impacts the dense gold-platinum test mass, it has a chance to be stopped, depending on its energy. As these particles are mostly positively charged protons, this creates an average net positive charge rate. Unfortunately, the test mass capacitive control and sensing system only works if the test mass is at or very close to the spacecraft ground. Not only is this a catastrophic controls issue if left unchecked, charges on the test mass can interact with stray electric fields of other componentry in the spacecraft via Lorentz force coupling. It is this noise source that we call charge-induced force noise. For a more detailed description of this phenomenon, see Peter Wass's presentation on cosmic ray test mass charging, or Samantha Parry's presentation on charge-induced force noise modeling, or both. It's up to you. Okay, so we have a problem that boils down to there being an uncontrolled charge on the test mass. Clearly we will have to deal with this. To complicate matters further, we cannot physically touch the test mass, as this would induce a displacement noise much greater than that we can accept. LISA is, after all, looking to achieve a displacement noise floor on the order of 1 picometer per root hertz, in the 10 millihertz range. Thus, we will have to do this remotely. A little like this conference, I guess. The solution to this remote discharging was first demonstrated on Gravity Probe B, and again on LISA Pathfinder. That solution was to use UV photons carrying an energy high enough to eject electrons from gold-coated surfaces, around 250 nanometers. It turns out there is a good reason that the test mass and housing are coated in gold, other than it being pretty. Shining these UV photons onto the test mass results in electrons flowing to the housing and positively charging it. Shining them at the housing instead gives the opposite effect. Naturally, it is a little bit more complicated than this. What happens when the UV photons hit both surfaces? This leads us nicely into the changes made since LISA Pathfinder. Now, while the results from the charge management system on LISA Pathfinder show that this method works as is, there are still fundamental changes being made to the new design. One of the main reasons for this is the extended lifetime required for the full LISA mission, rather than the relatively short duration of Pathfinder. What are these changes? Well, the LISA Pathfinder CMD design used mercury lamps to provide the UV photons, which are large, power-hungry, and complex to use due to their high voltage drive. The LISA CMD will instead use a new technology, UV LEDs. For details on how UV discharging works, and measurements of the effectiveness of UV LEDs, see Taiwo's presentation. For details about the UV LEDs themselves, and our in-house lifetime testing campaign to space qualify them, it's pretty crazy. See Ben's presentation. The use of these LEDs not only reduces the size, mass, and power required, but also allows for high bandwidth pulse modulation. This modulation allows the total on-time of the LEDs to be reduced, and increasing the dynamic range of the UV power, as it provides another knob to turn other than just the LED current. Remember the complication from before, where the UV light didn't necessarily hit the surface one might expect? Possibly due to gold being reflective? Maybe? Well, this high bandwidth allows the UV LEDs to be pulsed in sync with the 100 kHz test mass sensing field, thus allowing fine control over the direction of the charge distribution when all surfaces are illuminated. It is for this reason that there is a third injection port that purposely does this. For more details on both DC and AC pulse control, as well as the results of tests with our in-house torsion pendulum, see Stephen's presentation. Alright, now it is time to get specific with the design requirements for the CMD, as well as the budgets we must work within. Let's start with the highest level requirements, which will flow down to lower level requirements. The LISA CMD shall deliver UV photons to the test mass. Wow! It shall be able to do this in either intermittent or continuous discharge modes. That is either during pauses in the LISA's observation run, or continuously during science observations. The CMD shall illuminate the test mass in either DC, quasi-DC, or pulsed mode. That is when the LED is either on continuously during a discharge session, partially on during a second, or when pulsed in sync with the 100 kHz test mass sensing field. Before we start, let's get a few acronyms out of the way first. The CMD is made up of two parts, the fiber optic harness, or FOH, and the UV light unit, or ULU. We will get to these soon. Next up are the inertial sensor ultraviolet kits, or ISICs, which are what the ends of the FOH connects to in order to shine the UV light onto the test masses. There are 3 of these per GRS head, one pointed at the test mass, one at the housing, and one at both. Finally, there is the movable optical subassembly, or MOSA, which contains all the optical bits that can move. The GRS is one of these things. Also, remember that you can pause the video if you want to read anything in more detail. I'll throw this symbol up when I recommend you do. So, the requirements. First up is that the CMD must deliver light of the correct wavelength to the GRS head itself, and it is this job that is carried out by the FOH. The FOH connects the ULU to the GRS ISICs through the MOSA interface. Now you see why I have to explain the acronyms. It must also be able to do this in such a way that the 3 ISICs per GRS can be illuminated simultaneously, while still being controlled independently. The fiber delivery system has the requirements seen here. Next up are the pulsed operation requirements. In pulsed operation, the CMD shall control the UV pulses with 4 independent controls. These controls are the peak UV power, the phase delay relative to the ejection electrode, the pulse duration, and the number of pulses produced per second. The pulse requirements are shown here. Finally, there are the DC and quasi-DC operational requirements. The quasi-DC operation can be thought of like an extension of the pulsed operation, but with using a 100% pulse width and merely controlling the pulses per second and the peak power. The requirements are shown here. Now, the budgets. This is a little simpler. These make sure we don't make something the size of a car that requires a 3-phase power outlet. So here are a few of the big ones, for the size, the mass, the power, and the temperature. It's time to get to the main event, our current Tier 05 CMD design. And it begins with the UV LEDs, as it is these that form the core of our system. Looking at the spectrum of a batch of LEDs from Crystal IS, while running them at DC 20 mA, we see that on average they emit a peak of 250 nanometers. When we look at the same batch of LEDs at the same current drive, but at a 1% duty cycle at 100 kHz per pulse rate, or 100 nanoseconds, we see that the spectrum barely changes. Shown here is a plot of many UV LEDs from multiple manufacturers and batches, showing the average voltage and currents required to drive them. As I have previously mentioned, if you'd like more information on these guys, see Ben's presentation. As you've seen before, we need 3 LEDs per GRS head, and there are 2 GRS heads per spacecraft. Thus, we will need to house 6 in total, along with a way to monitor each of their performances. So, let's put this guy into a housing, along with another 5, each with its own photodetector for power monitoring, heat sinks with temperature probes, a wiring distribution board, and a snug lid to form a hermetically sealed environment. After closing up the purge valve, we can see that on the front we have the connectors for 6 FOH optical plugs, used to deliver UV light to where it needs to go. And there you have it, the optical mechanical assembly, or on me. Okay, so we have a housing for the LEDs, but what about a way to drive them? Allow me to introduce the UV LED driver board, or UVDB. You can drive 3 LEDs independently, each with their own peak currents formed into the required pulses. It monitors the photodetector and temperature probes inside the OMA, the number of pulses that it is producing, and the average voltages and currents that it is generating. Some examples of those currents from our version 1 UVDB are shown here, as we are currently in the process of assembling and testing a lower noise version 2. These are current pulses produced by the UVDB for a 10% duty cycle pulse at 3 different current settings of 12, 20, and 24 milliamps. The resulting optical pulses are shown here. While the optical pulses you may get may not line up exactly with what was asked for, the differences are systematic and can be adjusted via a lookup table if needed. Okay, back to non-reality. The UVDB itself sits in a tray to give it rigidity and to keep it cool. Since each one drives 3 LEDs, we will need 2, which are then bolted together and fastened to the back of the OMA. This then forms what we call the LED electromechanical assembly, or LEMA. Cool, what's next? Well, how about a way to control all the things? For that, we have the digital control board, or DCB. At its heart is an FPGA running in sync with the spacecraft clock and communicating with the spacecraft instrument control computer, or ICC. It produces the trigger signals that command the UVDB to produce the pulses of peak current that it also sets, according to what it's been told to do by the ICC. It reads all the health telemetry data by polling the UVDB and PV, we'll get there, and sends it to the ICC as often as required. Now, the current DCB doesn't quite look like the design here, for a couple of reasons. The first is that it's still under testing. Currently, the firmware is being completed to bring it all online bit by bit. The other reason is that the space-qualified FPGA is really expensive. So, to reduce our collective anxieties, a firmware-compatible commercial off-the-shelf version is being used during development. The board is designed to be operational with either being soldered in. Okay, now let's get back to it. Like the UVDB, it also has its own tray, together forming a control module. At the front of this module is the I/O required to interface to the spacecraft clocks and to the ICC data bus. I said PB before. Can you guess what that stands for? Top marks. Powerball. Give yourself a pat on the back. Well, there isn't much to this one, but that doesn't imply it's not important. It takes the 50-volt spacecraft power rail and down converts it to all the internal rails needed by the UVDB and DCB to run the show. It then offers the DCB readings of its voltages that it is producing, the current draw on each one, along with some board temperatures. And here it is in its current testing state. You can see that, like the DCB, some cost-cutting measures have been made during the testing and design refinement that allow a lab power supply to take the place of the expensive space-qualified DC-DC converter. Okay, back to it. Just like those boards that it enables, it fits into a tray to create a power module. Obviously, there must be a way to connect all these boards together, and of course there is, in the form of what we call the backplane. This board sits at the back of the ULU housing, which itself contains rails for each of the modules to slide into and mate to the backplane, connecting them all together. Hold on now, what about the other half? Well, after putting the center ribbon to separate the two halves, we can install the fully redundant modules. These are identical copies of the main modules, all connected to the same backplane board. This allows for redundant cross-strapping. For example, each power module can fully power the system in the case of an issue with the other. Each LEMA is cross-strapped through the FOH to both be able to illuminate the same 3 ISECs in both GRSs, with each UVDB pair to be able to be powered on and off as required. Finally, each DCB can address either UVDB pair, depending on which is currently set active by the ICC. Right, so after closing this up, we have the UV light unit, or ULU. Together with the FOH, this forms our current design of the UF TRL5 charge management device. And that's about it. Thanks for making it this far. If you have any questions, feel free to leave them below. Hopefully you found this video informative, or at the very least interesting. Just like the segue to our sponsor. I'm kidding. See you later.